first section in Chapter 6 is all about the elements. So we'll go through and talk about the development of the table. Scientist Dmitry Mendeleev that developed one of the first big deal periodic tables. And then talk about how things have changed over time, and then get into the different areas or regions on the table. So that's the plan for the day. So early on, before a periodic table was actually formed, we only had a few elements that existed, about 10 to 15 of them, and the elements from just a really long time ago up through the 1700s. The main elements were those like gold and silver and iron, those types of elements that were either valuable or they were used to make tools, the shiny stuff that we could actually make use of. So there's not really any need for a periodic table if you've only got that many elements. But starting in the 1700s, that's when alchemy kind of changed over to chemistry. And at that point in time, there was a major push to discover new elements, especially into the 1800s. It's kind of a big deal if you discovered an element. And so there was a major push in the scientific field in order to do that. And over a fairly short period of time, it went from double digits, the 10s to 20s of elements, up into the 20s to 40s, and then that increased even more up through the 1850s or so. Now there's some other things that happened, but we're kind of moving forward up through 1869. To a Russian scientist, his name was Dmitry Mendeleev, and the prevailing kind of thing at the time with a lot of different scientists would be to take all of the existing elements. And at that point in time, all we had for the elements themselves, for like carbon, for example, was a mass. So carbon's mass would be 12. You've got oxygen's mass, which was 16. But that's the only information that we actually had on each element. Now that was valuable in itself, but we didn't have the other information that you see on your current periodic table, namely the other number up here. So carbon's other number is 6, and oxygen's other number is 8. Calcium's other number, you've got about a 40-ish and then a 20-ish. This other number is the atomic number, and that's the number of protons. And Mendeleev didn't have that to work with. All he had was mass, atomic masses. And the main reason, if you remember from the last couple of chapters, was that we're dealing with 1869. And so this was right about the time from here into the early 1900s. That's when the number of protons and neutrons and electrons, that's when those substances were actually being developed, or those were being researched. We were discovering with like J.J. Thomson with the electron, for example. So he didn't know that there were actual subatomic particles that existed, and so he used masses to develop his periodic table. And it looked a little bit like this. His was in Russian, of course, and so this is a translated version, and his looked a little bit different. Feel free to Google it. But most of the scientists, what they did was arranged elements by mass, and then some of them actually put them together into rows and columns. And for the most part, they just kind of squished all those elements together. And so there were some spots on the periodic table where properties and things like that, they didn't necessarily match up, but they just thought it was a fluke in the data. One of the key components to Mendeleev's table was that he actually left blanks. For example, like right in here and here. You don't actually see any element symbols because those didn't exist at the time. But Mendeleev, he recognized that there were patterns that existed in his periodic table. And if you look at your periodic table, for example, you've got lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. Those are elements across, including lithium, across the second row on your periodic table. So what we're talking about is beryllium, boron, carbon, nitrogen, oxygen, fluorine. Those are those same very elements that you see on this table here. And then the next column down, I've got some copper and some zinc and a blank blank arsenic. And here you can see copper, zinc, blank blank arsenic. Most scientists didn't actually leave those blanks there, but what Mendeleev proposed was that the reason why the trends in the periodic table, why they didn't actually work out all that well, is because there are elements that exist that have yet been discovered. And so he left blanks on his periodic table. He knew the data on this periodic table front and back. He was very diligent about things, and so a combination of knowing things better than most other scientists and then leaving those blanks in there, that basically is the reason why he is credited with creating the first periodic table. There were other periodic tables that existed, but if you're looking at the father of genetics is Mendel, the father of evolution is Darwin, not because they did like things first, but because they kind of pushed forward with extra information. So the father of the periodic table is considered to be Dmitri Mendeleev. So fast forward 50 years-ish, we have now discovered electrons and we've discovered protons. And so Moseley in the early 1910s in 1913, he determined the atomic number for each known element. And this table that you see on the screen here, this is way more elements than were known at the time. You can see that down here we've got some of the brand new ones, and those have since been given names as well. So he arranged the table with this new data, this new information, this atomic number. And so that's how we run it now. And as it turns out, Mendeleev's table, including the elements that exist here, and then our current periodic table, which is now arranged by atomic number, there are, for the most part, overlaps in how it looks. And I'm just going to zoom in for a second here. There are a few certain spots on this periodic table where things don't match up. So for example, if this periodic table were arranged by increasing atomic mass, there are spots that would need to be switched. And I'll point out this area over here. You have tin, whose mass is 118, antimony, whose mass is 121, tellurium 127, and then iodine is 126. So if this were the old table with mass, this element and this element would need to be switched if this were Mendeleev's table. But they're not. And it makes more sense now that you have some knowledge about electron configurations, and you know that all of the elements in this periodic table, they end in the electron configuration of p5. So for example, fluorine is 1s2, 2s2, 2p5. And then chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So all of these elements, now that we know about this, they all have the same last part of their electron configuration, which really gives each element its own unique properties. And so it makes more sense that you line up elements vertically with that same information. And so we have the table that's slightly different. And when you do arrange elements like this, every eighth element, every octave, for example, which Newland kind of proposed, you have, when elements are arranged in this way, there are patterns. There are physical and chemical patterns that emerge, and everything lines up. And so lithium behaves a lot like sodium, which behaves a lot like potassium, and beryllium is similar, and magnesium is similar. So elements that are in the similar area on the periodic table, they have similar patterns. And that exists throughout the whole periodic table. And that concept is called the periodic law. Super important concept behind the periodic table and how it's arranged now. So that's a key point, a key piece of information that you need to know. One, the periodic table is arranged by atomic number, or number of protons. And two, the periodic law exists because elements are arranged by atomic numbers. So there are chemical and physical patterns that emerge when our table is set up like this. Now, you're probably not quite familiar with a lot of these trends, a lot of these things that happen over and over on the periodic table, just because you've not had exposure to it yet. You don't know necessarily necessarily how to read the periodic table really, really well yet, but part of what chemistry is all about is getting you to be able to kind of interpret the periodic table for what it is. Okay, so that is the first major concept, first major topic. As you know, down at the bottom of the periodic table, we've got the lanthanides, which are named for the first element here, lanthanum, and the actinides. These elements, when you guys were working on electron configurations, I pointed out the fact that you go from barium, which is element number 56, down here to lanthanum, which is element number 57. So when you're keeping track of your electrons, you kind of have to do a little coda, or a little jog down here, and then you go through this group, through this horizontal row. And then you got to go back up here, and then go back through your D sublevel here, and then all the way through the end, and then number 87 and 88, and then once again you jog down here to 89 and all the way through. So actually, if you're looking at a periodic table, if it were arranged truly correctly, your periodic table would actually look like this. But this is difficult, because what this does is adds some significant width to your periodic table, to the point to where it doesn't fit on a piece of paper well. And you could shrink it down, of course, but then the numbers get difficult to read. And so what we've done is taken this group, the F block, that I've called it, taken this block of elements and just cut it and then pasted it down here. And what that allows us to do is slide all of these elements just kind of slide down. And this is your D block and your P block over here. So this is how the periodic table would actually look. Now, in addition to having substances that are solids, liquids, and gases, we also have sections on the periodic table that have their own kind of common properties. And the first group is metals. And metals have a set type and number of properties. There are lots and lots and lots of them. But included in them, most metals are super shiny. And when you think about like gold jewelry, platinum jewelry, copper wire, those kinds of things, most of these metals are going to be shiny. They are good conductors of heat and electricity. This is why your pots and pans are made of metals. This is why copper is used for electrical wiring in your house. If you've got some high-end stereo equipment, those oftentimes the ends are tipped in gold so that they can conduct a little bit better. Almost all of the metals are solid at room temperature. The only one of the metals that's not a solid at room temperature is mercury, which is a liquid. And then they are also malleable and ductile, and when we talked about intensive properties, extensive properties, physical properties of elements, these malleable means it's able to be hammered out into sheets, and then ductile means you're able to make things into wiring. So those are some additional properties of metals. And normally if a substance is malleable, it is also ductile, but if you think of like gold foil, aluminum foil, copper wiring, that kind of thing, those properties are for metals. Metals in general are found on the left side of the periodic table and the middle of the periodic table and the bottom of the periodic table, and I'll show you that in a color-coded version here in just a second. So opposite of those are the nonmetals, and if you take all the properties of nonmetals and just say the opposite, that's really what nonmetals are. So they are not lustrous, not shiny. They do not conduct electricity very well. In the nonmetals, you've got some gases, you've got some solids, and then the other liquid on the periodic table, which is bromine, that one is a nonmetal. And what you see here in the picture is some sulfur, which is very brittle. If you were to try and hammer out sulfur into a sheet or into a wire, that's not going to work. It would just shatter. And then the last group of elements on the periodic table are the ones that are kind of in between. Semimetals, they're also known as metalloids. Those, they share properties, so both metals and nonmetals, kind of depending on the physical environment, it varies. So, color coding. If you need to pause this, if you're writing things down, then feel free. Otherwise, I'm going to move on. here's your color coding of your metals, your nonmetals, and your semi-metals. We have a periodic table in the classroom that's color coded by whether it's a solid, liquid, or a gas. This is yet another useful coloring. So as I had mentioned, your metals are on the left and the middle. Anything that's yellow in here is a metal. The only one over on the left side that's not a metal is hydrogen. It is element number 1. It's got its own space. You might notice that there's a little bit of extra space in here that's not over here. And that extra spacing that exists in here too. The hydrogen, that little extra space, it's supposed to represent the fact that hydrogen isn't amongst this group of metals. It's not part of that group. So it's kind of by itself. It's in the top left because it's element number 1. Then you've got metals all over the place, all the way over here. So the majority of the periodic table is made of metals. Over on the right-hand side, we've got our nonmetals, and those are color-coded blue. In kind of the quadrant of the top right, including all these guys over on the end, helium, neon, argon, krypton, xenon, and radon. Those compose the nonmetals. And as you know, helium's a gas, neon's a gas, argon's a gas, fluorine's a gas, oxygen's a gas, chlorine's a gas. Bromine is that liquid that I spoke of in our periodic table in the classroom. Bromine is labeled blue. The lettering is labeled blue. And all the rest of them are either green for gases or black for solids if you're looking at the periodic table in the classroom. But all these are nonmetals. And so we have a few of those. And then the last group are the semi-metals. And for semi-metals, I kind of think of this as an upside down triangle. You might want to take your periodic table if you've not done this yet and draw the stair-step line along these elements. So let's just start on the left side of boron and then just draw some stairs. That's all you need to do. And this is called the metalloid line. This is the line that separates the metals and the nonmetals. And every single element on the top of the line is a semi-metal. And then if I were building a pyramid, it's the middle 2 elements underneath the line that are also semi-metals. Okay? So those ones are the semi-metals. That line is going to be present on the periodic table in the classroom as well. So if you're not actually labeling yours right now, if you don't have a marker or a pen or something like that, or if you just want to wait till later, that's the stair-stepper line. And again, all the elements that are on the top of the line and then the middle 2 elements on the bottom of the line. There is, I guess, some debate on what the status of polonium is, whether it's a metal or a nonmetal, but it's commonly kind of agreed upon by most scientists that polonium is in with the metals. Here's, on this periodic table, I'll point out as well, I was talking about Mendeleev a few minutes ago. He had copper and then zinc and then skip, arsenic. He left blanks here for these 2 elements. He predicted the properties of these elements. And then later on, as it turns out, the properties matched up exactly with the elements that Mendeleev left a blank for. So that was a testament to his knowledge and his dedication to the making of this table. All right, so that takes care of sections on the periodic table. Next thing I'm going to talk about is some individual groups on the periodic table, and we've got these vertical columns on the periodic table, and then we've got horizontal rows on the periodic table as well. And so I'll go over those just a little bit. And those are grouped together on purpose as well. Any square on the periodic table, it's going to need at least 3 things. What you need is the element symbol, the atomic number, and then the atomic mass. In this atomic number and mass number, it actually should be atomic mass. Because mass number is unique to each isotope and is going to be a whole number. The number that you see on the periodic table is decimal number, which is technically average atomic mass or atomic mass, what used to be called atomic weight. Okay? Most periodic tables also have the element name on there as well. This is helpful if you've not used the periodic table before, especially helpful if you don't know about all those weird new elements that exist, whether it's TS or OG or LV. A lot of those we don't necessarily use regularly, and so it's helpful to have the name there as well. So, organizationally speaking, there are 18 vertical groups on the periodic table. And those vertical columns are called groups, and they're also called families. Those are common. Either one is going to be fine. You can use the word groups or you can use the word families, and it's just great. Either one is equally correct. And then the other set are periods, and these are the horizontal rows. And there are 7 of those. 7 periods. And earlier on in the year, I had you label these when we were talking about shorthand electron configurations. You've got the hydrogen period, lithium period, sodium period, potassium, rubidium, cesium, and francium. All those periods from left to right. There's 7 of those which correspond to the 7 different energy levels when dealing with electrons. Got a chart there that doesn't want to show up. There we go. So if you look at row number 1, horizontal row number 1, there's 2 elements in there. You got hydrogen and you got helium. For number 2, you've got 8 elements. In the second period, you got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And then in the next period, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, which is 8. Next group down, you've got 18. And then in the next group down, you've got 32. This does match up with your energy levels. If you remember, energy level number 1 equals 1. That is a 1s, which fits 2 electrons. In the energy level number 2, or n equals 2, you've got your 2s and 2p. And 2 electrons fit in there, and 8 electrons fit in there, and that's where the 8 comes in. The third energy level has 3s and 3p and 3d. Remember that d's fit 10s, p's fit 2. Oops. And that's where the 18 comes from. Remember the 3d is dropped down, so it doesn't show up in the second period. So all of those things match up from earlier on when we were talking about electron configurations. And that's the reason why the periodic table is arranged in that way. All right, switching back to vertical. Groups on the periodic table, they are numbered in a variety of ways. Oops, wrong keystroke button there. I'm going to back up. Don't get dizzy here. Backing up, backing up, backing up, backing up. You can see that the groups on the periodic table, they are numbered from 1 all the way through 18. From 1 through 18. And that's the easiest way to label things. 1, 2, 3, 4, 5, 6, all the way through 18. You can see that there are also 1A and 2A all the way through 3A, 4A, all the way through 8A. And then we've got some B's as well. 3B, 4B, 3A, 4A, 5A. We've got B's in there and A's, and so it gets a little bit confusing, especially if you're using Roman numerals. And the blue parts, they're a little bit goofy, but we've got that one actually is, these are supposed to be B's here. B, I don't know why this one has the A's. 3B, 4B, 5B, 6B, 7B, and then you got some AB, as you can see here. So the actual numbering is the right way. The Roman numerals, they kind of swapped them out. Now I don't know why they have 3B through 8B, and then you got 1B and 2B. I'm not real sure. What I just recommend is you just use the regular numbers, 1 through 18. That's just a whole lot easier. You don't have to worry about A's and B's. So it's just easier to understand. All right, moving ahead. Those numbers, 1 through 18, they also have names as well. And so group number 1, those are called alkali metals. Special name for them. You should know this name. Group number 2 are the alkaline earth metals, and unfortunately your alkali and your alkaline or alkaline, they all look the same. the words look very similar to each other, so that's a little bit difficult to remember. Alkali metals include lithium, sodium, potassium, rubidium, cesium, and francium. Do not put hydrogen in with the alkali metals. Lithium all the way through francium. And then the alkaline earth metals are beryllium all the way down through radium. They have their own special names on the periodic table. Group number 17, those are called the halogens. They have their own special name as well that you're going to need to know. And then group 18 are called the noble gases. Various reasons why these groups are named in this way. You can feel free to just Google it if you want. The noble gases, I'll point those guys out in their electron configurations, and that their S and P sublevels are full. So the 1s is full, the 2s is full, and the 2p is full, and then the 3s, 3p is full, and the 4s and 4p is full. This is the most important factor in determining stability. And all of these, helium, neon, argon, krypton, xenon, and radon, all of these elements are ultra stable. It's the reason why this group was the last to be discovered, because if they're ultra stable, they don't actually do any reacting. All right, some other sections on the periodic table. We have the representative elements. Those are group 1A through 7A. So if you're looking at the periodic table, this is groups numbers 1 and 2, and then 13 through 18. So those are basically the tall columns, all the tall columns except for the noble gases. Representative elements, because they represent the variety of properties or characteristics that exist with all of the different elements. We got some solids in there, we got liquids, we got gases, we got metals, we got nonmetals, we got semi-metals. There's a little hodgepodge of pretty much everything from the periodic table in there. We've got another section called the transition elements, and these are found in the short columns on the periodic table. This is groups numbers 3 through 12 on the periodic table. And so those are the elements that start with scandium and titanium and vanadium and chromium. These are basically the D block. Elements that have electron configurations with a D ending. So your 3D, your 4D, your 5D, and your 6D. Those are the transition metals. And then, speaking of the little coda or the little jog after barium, you have to go down to the bottom of the periodic table to lanthanum, and then go through and then back up again. And then in period number 7, you got francium, then radium, and then you jump down to actinium all the way through, and then back up again. Those elements are called the inner transition elements because they're kind of inside the transition elements. So these are from periods numbers 6 and 7. In between the S and the D block. So this is in period 7, this is the F block. These are elements whose electron configurations end in F something. So we've got those. Just to review, we've done this already, but as far as the periodic table goes, groups numbers 1 and 2 are the S block because they end in S1 and S2. You've got your P block over on the right-hand side, which end in P1 through P6. Your D block, which elements end in D1 through 10. And then the F block, those elements end in F1 through F14. To finish things up, there are groups on the periodic table that exist that have other names, and then some of them have special names as well. For those particular elements, you can just call them the first element at the top of the group. So group 13 can be called group 13 or the boron group. Group 14 is called the carbon group.
Alexa,
Group 15 is called the nitrogen group. And then group 16, those are called the chalcogens. They mention this in your book, but not necessarily in a lot of your homework and stuff like that. Also called the oxygen group. I'm not going to worry about the chalcogens, the wording of that for homework and test purposes. This is just an FYI to let you know that that exists. So if you see the word on some of the activities that we're doing, that's where it comes from. So hopefully this was helpful, and you can work on some of your homework assignments and study for the test from this information.